So today we thought of starting up the classification models. In the classification models, we are required to touch different types of classification models, out of which logistic regression. So basically this looks like the logistic regression looks like a regression model, but actually it's not. The logistic regression represents a regression model, but actually it is a classification model based upon the, by name itself, logistic, which is a two separable logical related problems kind of stuff. Okay, so now one more thing that we have to understand here is we have something called a KNN classification, name base classification, decision trees, random forests, and SVM. Okay, we have different algorithms to work on this particular classification models, guys. Okay, as a part of this, but before I'm going to discuss something about this one, see that these decision trees, okay, random forests, bagging, and boosting will come under this different segment. So I'm just making two different segments. What I will do, I'll first cover these four, and then I will then go ahead for these four. Okay. So before I'm going to cover something on this particular classification models. I need to explain you about something called some basic concepts. Scaling, scaling. Otherwise, we will generally call it as a feature scaling. And next one is confusion matrix. Okay. So now coming to the feature scaling. What do we mean by scaling? Scaling is none other than that we can quite relate to a concept in statistics that is none other than normalizing the data, normalization. Now, can you please recall something related to the normalization that we have discussed during the statistical part? Let me see how many of you can recognize it and how many of you can give me the exact formula of the normalization. Anyone can recall it, guys? No one. So let me explain. First of all, I will definitely make you to remember when I say normalization or the standardization, is it not something related to the standard normal distribution and the normal distribution, guys? Is it or is it not? It is x minus x bar divided by sigma. Can you recall it? X minus mu divided by sigma. Z is equal to x minus mu divided by sigma, which is a standard normal distribution that we went ahead. But here We will just generally discussing apart from all this kind of stuff. How many of you can recall x minus mu divided by sigma? We have used this one in order to convert the given set of data into the standard normal distribution, and we will guess it as a standard normal distribution, and then we will resolve the issues. Can you all recall it? Okay, fine. That's okay, fine. We have done that one anyhow. Narayana, can you recall that one? Z is equal to x minus mu divided by sigma. Yeah. So now how we are relating that, how we are how are we relating that part to this existing scenario at this point of classification algorithms is very much important for us. Now, why we need to do the scaling? First of all, before I'm going to talk about this one, why we need to do the scaling of data set. So guys, I'm just wanted to highlight the things when I'm talking. See, when I'm working with a data set, definitely whenever we have some of the features which are highly variating within itself, like in magnitude or range or something else, whatever it is, number of units or whatever it is, means nothing but I can simply tell you in one particular word: high variation in the variables or the features that we can call. Generally, what does will do? There is a scatter plot, guys. You just wanted to segregate that scatter plot. You need to understand something out of it. Generally, we do go for the KNN method. KNN method. Okay, KNN classification by identifying the nearest neighbor using the Euclidean distance, which I did not cover it so far, but still I'm just mentioning it. Okay, here in the classification, most of the machine learning algorithms use the Euclidean distance between the two data points in their computations, basically. But when it is taking such kind of data points distance, those algorithms will take only the magnitude of the features, but not the units. Units represents, for example, one of the variable is consisting something called 10, and another variable will start from 1000. Okay, so these kind of features. Okay, for example, one more thing, there are two different types of weights. One will go ahead with, see, otherwise, you can represent a weight in 5 kg, and also you can represent a weight in 5000 grams also, right or wrong? Now, can you please tell me the features with high magnitudes, can't they weigh more than what they are in the lower magnitudes when it comes to the distance calculations, right or wrong? See, I have mentioned one particular column which is saying weight. I have represented with something like this. Okay, and then I have just represented something like this also uh, in the one more data set. What is the easiest calculation for us? First one. So hence this kind of things that we can understand. This is why scaling is required. Okay. Why? Because high magnitudes will give us the more weight than the low magnitude levels. So in order to suppress this one, we need to bring all the features to the same level of the magnitudes. Okay, this can be achieved only using the scaling. We can bring down all the things to the same level of the magnitude only by doing through the scaling. Understand? Here, there are 4 different methods in the feature scaling. Okay, scaling the features. Features are none other than the predictors anyhow. The very first one is standardization. Next one is mean normalization. The first one is standardization, and next one is mean normalization, and then the next one is minimum maximum scaling, and then unit vector. Okay, so what are all these different kinds of scaling methodologies that we do have? Let us understand. Whenever you are thinking about the standardization, guys, what this will do, the standardization will replace the values with the Z scores. This is what we have done, right? What is the Z score formula? Z is equal to x minus, it will apply the same, x minus mu divided by sigma. Okay, we know what are all the things and all stuff. Okay, so what about the mean normalization? See here, we should understand for the standard normal distribution. When when you say that it is a standardization for the standard normal distribution, okay, it will redistribute the features with their mean value, which is mean is equal to 0 and sigma is equal to 1. Understand? So it will take up something like that and then it will perform. It will redistribute the features with their mean is equal to 0 and sigma is equal to 1. So now, mean normalization. What do we mean by the mean normalization, guys, here? Whenever you have, for example, you have got something like this. So mean normalization, sum y equal to x minus mean of x divided by max of x minus minimum of x. This is the mean normalization. This is one type of normalization. Okay. So here we need to understand one thing. Here the mean mu is equal to 0 and always the distribution will lies the values in between the minus 1 and 1. And here the standardization and the mean normalization will be using it something which is relative to the principal component analysis. Right. No, 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 no. It's not. No, 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 no. It's not about the sigma x. It's not some x. For the individual values of normalization, we are not making a sum x. Max of x means higher value of x. Minimum of x means minimum value of x. Mean of x means taking the average of all the values of particular x values. X represents only a single value. right? Starting x. Okay. And coming to the minimum maximum scaling, generally what happens with the minimum maximum scaling? It is also looks like the same, but the only difference is, let me just show you. Instead of mean, you will have something called minimum. That's it. That's the only difference. And here in the mean normalization, here generally standardization and the mean normalization, we will generally use it in something called a principal component analysis. Okay. And now here minimum maximum scaling will rely on something called, it will get you the values between 0 and 1. Okay. These values will be in between -1 and 1. Okay. And these values will be between 0 and 1. What about the unit vector? Unit vector is very simple thing. Some y is equal to, y represents nothing but an x actually. Okay, otherwise I can call something like this, x. Why? Because we are scaling this one, right? I'm just wanted to change instead of z. Let me make something like this. So x represents x divided by modulus of x. So here the minimum maximum scaling and the unit vector produce the values between 0 and 1. Also, when dealing with the features with all the hard boundaries, will definitely work out with this one. For example, when we are dealing with the image data, all the colors will range from 0 to 255, right? Okay, there we can normalize something like that. Okay, so now we understood like what are the different types of scaling that we can perform and why the scaling is required. But when to scale, you need to understand that part also, right? See, whenever you are using k nearest neighbors with an Euclidean distance formula, which is very sensitive to the magnitudes of the values for your variables. Hence, that needs to be scaled for all the features to weigh equally for all the variables or the values. Okay. And also this needs to be applied for all the tree-based models. Why? Because tree-based models are not the distance-based models. They have to get handled in a different way based upon the probabilistic stuff. And the scaling definitely will not be required. This kind of scaling will never not be required in that particular model. But rather, we could definitely, uh, whenever we are working with linear discriminant analysis or the principal component analysis, will have the maximum variance for the high magnitude features, which will keep the, when we have the high magnitude features, either we will experience the left skewed or the right skewed, right or wrong. It's all about the values, guys. So in order to suppress that one, definitely we require this kind of scaling, which is critical for it. And also gradient descent. Gradient descent is something just like to identify the right weight at the right point, which we did not discuss that, which needs to be discussed. So this can speed up the gradient descent by scaling. Okay. So we can perform the scaling for our flexibility in order to get more understanding about the kind of stuff that we are looking forward based upon the normalization of all the values that we do have. Okay. Are you good so far? Okay, now coming to the confusion matrix. The confusion matrix is the one which is very important to understand, first of all, which will help us to understand the classification models and its performance, how it is, how they are performing well and all stuff. But before that one, we need to first understand what exactly the confusion matrix and how could we can resolve this. Now, to understand more this one, first of all, what could we say about this regarding? Hmm? See, confusion matrix in the machine learning will be more worthful if we just want to use something related to the classification model. Okay. Sometimes we can call this confusion matrix as something called an error matrix. Okay. What it will do, it will give you the prediction results. Let me just showcase you this way. Before I'm going to explain the example, let me just first explain you how exactly this confusion matrix looks like. It depends upon, it will just classify as how many correct predictions have been made based upon the training data. How many incorrect predictions have been made can be clearly understood from this particular kind of confusion matrix. Okay. This is really, little bit looks like tricky, but still we should not get confused. That's why I'm just taking this session to explain you these concepts. Why? Because you should not get a doubt when I'm going to execute a query tomorrow for each and every. Why? Because KNN will definitely consider the scaling. Whenever it is required, we will do the scaling. Okay. So if you can take a look at this one, I just wanted to mention you something before I'm going to explain you this part. First, you need to understand what do you mean by P. Whenever your observation is positive, then we can consider it as positive. What do you mean by N? Whenever your observation is negative, we can consider it as a negative. What about the TP? Represents true, positive. What happened? Huh? Oh my God. True, positive. Hmm? And then, what do you mean by FN? False, negative. Okay. TN, true, negative. FP, false, positive. Hmm? Okay. So now, before I'm going to talk about something related to this one, we should be knowing all this kind of stuff. Okay. Right. So now, how we are going to understand this one? Classification rate or accuracy. We can determine this classification rate or accuracy something like this. TP plus TN divided by TP plus TN plus FP plus FN. Okay, all the true positive plus true negative divided by true positive, true negative, false positive, and false negative. All of you understand this one. So, however, all these problems with the accuracy, we will assume equal cost for all the kind of errors, and we will be why? Because whenever we are doing like this, there will be an accuracy rate, whatever that we are trying to identify, will give you some sort of percentage. Okay, whenever it is 99% accuracy, that it is that we can say that it can be excellent or good sometimes, depending upon the problem. Okay, we have to ensure that the how exactly the problem data set it is and all stuff. So here we need to understand before I'm going to talk about rest of all the measures that we can do. Why? Because there are four other things that I just wanted to consider here. Rather, otherwise I can say that we understood the accuracy. Apart from accuracy, we have recall. What do you mean by recall? And what do we mean by precision? Okay. And also what do we mean by F measure? Okay. So this recall and precision and accuracy is very much important here to understand. Okay. Now coming down, see, I'm going to take an example here. Okay. I'm trying to understand with an example where the example says we do have couple of elements in the class A and class B. Okay. And when I have taken like 165 elements across, I am going to get the results of something like this, where I just wanted to highlight them in order to take a more brief about them intentionally. Okay. So here, otherwise, even we can take it out different problem or examples even. Okay. So here, let me just go ahead with the manual example before I'm going to try showing you this part, how well it looks like. Okay. So there is there is some data set. Okay, there is a data set which is consisting two columns. One is expected and another one is predicted. Okay. Whenever there is a man is predicted as woman. Okay. This is how the representation or the prediction happened. Let me tell you. Whenever there is a man, there is a prediction happened as man. Whenever there is a woman, the prediction happened as woman. Whenever there is a man, the prediction happened as man. Whenever there is a woman, the prediction happened as man. Woman, 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 man, 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 woman. So how many predictions so far? One, two, three, four, 5, 6, 7, 8, 9, 10. Okay, I got the 10 predictions. 10 only, right? 2, 3, 4, 5. 1, 2, 3, 4, 5. 10. 10 only. Okay. So now I just wanted to perform the accuracy on this one. Okay. So in order to perform the accuracy, we need to understand accuracy is equal to total correct predictions divided by total predictions made, right or wrong? So accuracy equal to how many correct predictions made? This one is correct. 1, 2, 3, 4, 5, 6, 7. 7 predictions are made correct. And then out of how many? 10 into 100 equal to how much? 70%. Right or wrong? So here we need to understand few more things like how many times the men classified as women and how many times women classified as men. Okay, so the arrangement of these values will be considered as a two class confusion matrix. Understand all of you guys? So here is the two class confusion matrix for us. So let me just show you. So here, man, woman, men, women. So can you please tell me how many men are predicted as men? 3. Okay. If you can take a look at this one, we can clearly understand man as man. 1, 2, 3. 3 times. How many times man as predicted as woman? 1, 2. Man as predicted as woman. Okay, man as predicted as woman. 2. Next one. Woman predicted as man. Only 1 time. Next one. Woman predicted as woman. 4 times. So now here comes the picture. From this table, we can clearly understand the actual men in the data set is the sum of values on the men column. Okay, means 5 men. Right? Actual men are 5. 5, 5. Column I'm talking about, men column. Okay. So total actual women are 5. So equal men and women 5. So the correct values which are organized in the diagonal line, men and men 3 and 4. Right or wrong? So 3 plus 4 is a 7. So errors which are made by predicting men as women than predicting women as men. Right or wrong? Predicting men as women is more than women as men. Okay, so these kind of understanding would come up using this particular confusion matrix, where you could identify the precision, how well it is predicting, and how often it is correct and all stuff. We will use the precision and the recall kind of stuff. Understand? So hence, generally we used to make up this one this way: true positive, false negative, false positive, true negative. Okay. This is okay. In this segment, I'm just representing in your wrong way, I think. Why? Because these are actuals, right? In our case, these are actuals actually. Okay. So in this case, then I need to shift this one like this. How many men are predicted as women? So if I just wanted to do this one, I need to make, first of all, we need to understand which is actual and which is predicted. So men, how many actual men are there? Then we need to change this part. This is 2 and this is 1. That's it. So then these are actuals, and these are predicted. Right? Will this suit here? Let us cross check here one more time. Actual men are 3 plus 2, 5. Okay, 2 men have been predicted as women. Is it right? Man predicted woman. Here it is there 1, and man predicted woman. Yeah, here it is there 1, and another one is here. This is fine. Yeah, and woman predicted as men. Only 1, right? So this is fine. And woman predicted as woman is 4, right? So now here we can clearly understand this is a true positive, false negative, and false positive, and true negative. Okay. So now we can also understand the recall, which defines the total number of correctly classified positive examples divided by total number of positive examples. So means, what do we do this one? TP. How much is a TP? 3. Okay. Total positive. And one more divided by TP plus FN. FN represents the false negative. Okay. So if we are coming out of this, you know, you will calculate the respective recall and the precision values in the same kind. Okay. Understand all of you? So we can, I'm sorry. So now we can understand. What do you mean by recall? As I told you, higher number of, so if you have the high recall, means you have most of the positive examples which are correctly recognized. Yeah, here actually what actually we cannot go with the false negative kind of stuff here. Okay, why? Because the one which I have explained you is a one class problems. Okay, what I am calling it as, no, we can call it as a two class problem itself. So these two class problems, let me just explain you. True positive, which is correctly predicted event values. Okay, false positive, which are incorrectly predicted event values. Okay, and true negative, which are correctly predicted no event values. Okay, false negative, see, you understood men actual is predicted as men, that is fine, Ashok. Okay, all of you. Now what about this false negative? False negative represents incorrectly predicted no event values. Means men is actual, but they have predicted as woman. False and negative. Woman is woman itself. Okay, woman is woman itself. So hence it is a true, okay, correctly predicted, no event values. Okay, no event represents the false. And whereas the, you can assign the column of predictions into the true. Woman as predicted as man, which is completely false, but it is predicted as man, positive. Any confusion here, guys? Ashok, did you understand? See here, the false positive represents incorrectly predicted men value. Okay, true negative represents correctly predicted woman values. False negative represents incorrectly predicted woman values. False positive represents incorrectly predicted men values. All of you understand this one? Ashok, are you good? If do you have still confusion, let me know. I will explain a new example in tomorrow's session. I will take up a new example and I will explain you if anyone have a confusion. Okay, so this is what it for today, and tomorrow we will just solve we will start off with the KNN model. Okay, classification. See you all. Bye.